we were on part B there, where it says use a graphing utility to graph a relation between the percentage of carbon 14 remaining and time. So we are going to graph this function. So we're building that function. So we know that n of t, we're starting with 100%. So I'm going to make that a 1, e to the negative 0.000121 t. Okay, that is what we're graphing. Okay, so I'm going to go to the calculator and I'm going to graph that. Why did I put a 1 there instead of another number? Because we had 100% originally with the carbon 14. Whatever time that thing was buried, that was when the carbon was 100% there. Okay, we found it when there was only 1.67% of it there. So we're starting with 100%. So I'm going to graph that, and I'm probably going to have to adjust my window because remember yesterday we had stretched that window out a big amount. Ours is not very big because we're starting with 100%. So we see it doesn't look like much of an exponential thing there. So I'm going to change my window to where I know my X maximum is going to have to be a really, really large number because half of the carbon is going to be gone at 5,730 years. So time is in years here. So that's my X axis. So I know my maximum on my X should be at least twice that. So 2 times 5,700. I'm just going to do 12,000. I think that's a safe number. Okay. And then my Y maximum, my Y minimum, I'm going to make it -1. And my Y maximum, I'm going to make it 2. Excuse me, sorry. And then hit graph. So I'm just making that Y value 2 so that I can see, the exponential decay. So we see it falling down into the right. Okay. Now, it says use a graphing utility to determine the time that elapsed until half of the carbon remains. So this is where half of the carbon remaining would be 0.5, 50%. And I'm going to hit graph. So this is where we're using that intersect idea. Okay. That number should be right on 5,730. Maybe not exactly because remember I rounded my decay rate. I had to round it at some point because it kept going forever. So I rounded it. So it's going to be really, really close to 5,730. So I'm going to hit second, trace, intersect. Yeah, it should be really, really close. Yeah, 5728 and a half. That's really close. Okay, so because I rounded it off, we lost a little bit there, but in the grand scheme of things, if we're off by a couple of years, over 10,000, that's probably not bad, right? We're not going to be perfect on that. So 5728.48. So C part 5,728.5. Or we'll do 0.49, I think is what you round that to. If you round it to 2 decimal places, yeah. 0.49. That tells us, hey, we did pretty good on our decay rate because it got really close to what the half life would be. It says, and then D part is compare those values. 5,730 is really close to 5,728.49. It just said compare those. That's all it asked us to do. Now, if they wanted us to find out how much, what the how old this piece was, so I'm going to add an E part to this. Okay, E part, how old is the wood. So if they ask us to do that, I'm taking that problem and setting it equal to 0.0167. And I could solve that with logarithms. Take the, divide by 1, take the natural log of both sides. I could also graph it. What do I need to graph as y2 and use the intersect tool here for this problem to solve that problem that I added? Not 1, because I'm trying to find out when there was 1.67% left. When I graphed the 0.5, I was finding when half of it is left. So I'm going to graph 0.0167. Okay, I see that's on off the page there. I need to go a little further with my window. I'm going to double that just to see if that gets us there. It may not. That's going to get us close. I think we need to go just a little bit further. I'm going to go to 36,000. Nope, 36 million, 3.6 million, but 36,000. See if that gets us where they look like they're crossing. Oh yeah, I got the cross. I can see the blue and dipping low below that, so I see the cross is happening there. So I'm gonna hit second trace, intersect, and then enter 3 times. $33,821 years old is supposedly how old this piece of wood is, based on carbon dating. Carbon dating used to be the standard, that they've come up with little better ways as technology has improved. They've come up with other ways, but carbon dating seems to still be a pretty accurate measure of things as far as how old it is. So 33,821 years old. We'll just go whole years there because I don't think we can estimate that. 800 and what? 21. So using that intersect tool can really help us in solving some of these problems out of that. So there is just finding how old the piece of wood is in that problem. Okay, so a pretty neat thing there. Finding that decay rate or that growth rate. So with a lot of these problems that you're going to see in the practice, you got to find that rate first and then use it to do the actual problem they're asking you to find, like how old something is or how much bacteria is there or whatever. So you got to find that rate first and then use that rate to help you solve the problem. All right, next thing is a pretty cool thing called Newton's law of cooling. So that is Isaac Newton, or Sir Isaac Newton, that we're talking about here. Newton's law of cooling said that if an object is heated and you get the temperature of that object. Mr. Isabel? Yes, ma'am. Reminder about your attendance. Thank you. Thank you. Yes, ma'am. All right, so if you've got things in this formula. So this formula, I'll give you this formula for the quizzes and tests, okay? Because it's quite a bit of stuff in there, okay? Capital T is the constant temperature of the surrounding medium. So that's like the room it's sitting in. So like if you set a hot cup of coffee in a room, T is the temperature of the room. That capital T is the temperature of the room, okay? U sub 0 is the initial temperature of the object you set down. So that's when you put that cup of coffee on the desk in here, that's the temperature that coffee was as soon as you set it down. Okay, that's the U sub 0, the initial temperature. And then the K here is your cooling rate. Every object is going to have a different cooling rate. Every person in here has a different cooling rate or heating rate. Okay? Because we're all made a little bit differently. Everybody's cup of coffee is made a little bit differently. Like if you put creamer in it. It's going to cool it off a little bit. So your initial temperature, it's going to change the viscosity of that thing. So everything's got a little bit different cooling rate out of that. So that K is your rate. T is going to be your time, usually in minutes or hours. Is how that works. So got a lot of stuff going on in this one. But the big thing is capital T. That's your temperature of your room you're in. Okay. Let me get attendance done real quick before I forget about it, because bless you. Because I'll get excited about this problem and forget. Because I like this one. This stuff's fun because y'all ever watch like the crime shows? All right, so one of the things that the crime shows, when there's a murder or something like that, is that they always try to find time of death, right? Because you got to create a timeline to figure out who did it. So time of death is determined based on temperature of the body when they find it. Okay, so they find the core temperature of the dead body, and they measure that, and then they let a certain amount of time pass, and then they measure it again, and they find out the cooling rate for that body, and then they can go from there and say, okay, now we know the temperature of where the body was left was this temperature for this amount of time, and then we can reverse engineer and find out how long that body's been there. Because when you're alive, your body's around 100 degrees Fahrenheit, that give or take. Everybody's is a little bit different. 98.6 is supposed to be normal, but core temperature is closer to 100 degrees Fahrenheit. So, yeah, it's very, very rare that 98.6 is your actual temperature ever. But somewhere around 100 is your core temperature. So inside of the chest cavity is where that's measured. All right. Attendance is done. So we can forget about that. All right, so I like the crime show. So this is what makes me excited about this stuff, because it's neat to see the math in action. So they take that and they figure out, okay, the body's been there 12 hours. Then that gives them a timeline, and then they know, okay, I need to find people that have an alibi for 12 hours ago, or if they don't have an alibi for 12 hours ago, or if they're in the vicinity. We can figure that stuff out. That's how we narrow down our suspects list and all that fun stuff. So this is the formula that can be used to do that. Okay, it's a pretty cool thing. All right, let's actually do something. This time we're going to be taking an object and we're heating it up to 100 degrees Celsius. What's important about 100 degrees Celsius? Boiling point for water, right? So if you wanted to heat an object to 100 degrees Celsius, you would just drop it into boiling water and leave it there for a little while, and it would eventually get to 100 degrees Celsius. It wouldn't go above that because water boils at 100 degrees. It's either boiling or it's vapor. It doesn't go above 100 degrees under normal conditions. Now, if you're in Colorado and around the Denver, up in the elevations, boiling point changes. It goes down actually. But if you're in Tennessee, you boil something in 100 degrees water, it's going to be 100 degrees. Okay, so we took that, whatever it was. Maybe it was, we boiled some soup and it was boiling when we poured it in the bowl, and then we allowed it to cool in a room whose air temperature was 30 degrees Celsius. If the temperature of the object is 80 degrees after 5 minutes. Okay, so we've got some stuff going on here. So A part, we're going to use our formula. Use U of T, capital T, plus U sub 0 minus T e to the KT. So this is the stuff we know. We know that the temperature of the room was 30 degrees Celsius. We know the initial temperature was what? 100 degrees Celsius, okay? And then that problem tells us that on A part, it says that the object is 80 degrees after 5 minutes. So we know T is 5 minutes, okay? We want to know when will the soup or coffee or whatever it is that we've got that was boiling, when will it be at 50 degrees Celsius? Because then we can probably drink it or eat it without burning our mouth. Maybe that's what we need. Okay. So first thing we needed to use is these three things, and that the temperature after 5 minutes was 80 degrees Celsius. That's going to help us find the cooling rate for whatever this object is. Okay, so I'm going to set up the problem with 80 equals 30 plus 100 minus 30 e to the k times 5. So I plugged in the room temperature, that's where the 30s came from, the initial temperature, that's the 100, and then after 5 minutes, that's the 5 in for T, and then the 80 is what the temperature was after 5 minutes. We're going to solve this for K so that we get our cooling rate for this particular object out of that. So let's do the math to solve this. So I'm going to simplify, make that 70 e to the 5k. Now let's go to work on solving this. What's the first step? Excuse me. Yeah, move that 30 over. Good. Move that 30 by subtraction. That's 50. We have 70 e to the 5k. What's next? Divide by 70. That's right. So divide by 70. Yeah, just leave it 5 over 7. E to the 5k. So that's a base e on the other side. So what do we use to solve? Natural log. So we're taking the natural log of 5/7. That's a number. Natural log of e to the 5k. What happens to our e and our natural log over there? They cancel out. That's the beautiful part of that. So we get 5k is equal to the natural log of 5/7. Divide by 5 is our last step. Whatever natural log of 5/7 is divided by 5. So go to the regular calculator screen. Natural log 5 divided by 7. Close the parentheses. Divided by 5. And I'm going to go 3 significant figures. So if you remember from science class, sig figs means the zeros in front don't count. So if I'm going 3 sig figs, this 0 doesn't count, that 0 doesn't count. The 6, 7, 2, that's 3 significant figures. So we're going to round to the tenths, hundredths, thousandths, 10,000ths place in this one. So I'm going 3 sig figs. So 9 makes the 2 go up to 3. So my cooling rate for this problem is negative 0.0673. That's a safe number. Yeah, that would be safe to do. I think that's going to still get you in the range of where you need to be. Best case scenario would be not rounding at all. But here I think 3 significant figures is going to get you enough, because all of these cooling rates are going to be nasty long decimals out of that. So you got to round them at some point. So 3 significant figures is probably safe. Okay. Now, that didn't answer the question that they asked. The question was, when will the temperature be 50 degrees? So now we know that U of T is equal to 30 plus 100 minus 30 e to the negative 0.0673 T. Now we need to plug in the 50. Where does the 50 go? Well, it can't go here because that's the room temperature. It can't go here because that's the starting temperature. It goes in this U of T. It goes over here. That's what the temperature is at the end. That's when we want to drink the coffee or be able to eat the soup or whatever it is. And I'm just going to go ahead and simplify there. Now we're going to solve again. So we're doing basically the same problem, just different numbers in there. And we're going to find T when we get done instead of K. because we don't know the time. We want to know how much time. Okay, so move the 30, same steps. Divide by 70. So we've got 2/7 equals e to the negative 0.0673 t. And then what do we do after that? Yeah, natural log of both sides. That's going to cancel out our natural log and e there. So we get the natural log of 2/7 equals negative 0.0673 t. Now all I got to do is divide by that negative 0.0673. And then that's going to get us our time. So I got okay. About negative point. Is that what you got? Okay. 6, yeah. And here I would round to probably 1 decimal place on the time because that's going to be like seconds, and we're not going to time it that perfectly, right? To get yeah. So 18.6 minutes is how long it's going to take it to cool off to that temperature. So we had to do 2 problems to be able to solve the one that they asked us about. Okay. It says in B part, use the graphing utility. So we did all this manually, which is absolutely a fine way to do it. And it's how I actually prefer to do it. But we can actually do this with the calculator too, using the same skills that we used earlier. So I'm going to type in the equation into my y equals menu. So I've got 30 plus 70 e to the negative 0.0673, and then instead of t, I'm putting x. Let me graph. I'm going to have to adjust my window because I know I'm not going out to 36,000 minutes. I would say I only have patience to go out to an hour, probably. Right? I'm probably not going to sit there and wait on something to cool off for an hour, more than an hour. Yeah, but 60 minutes is probably a decent number. And then my Y's, I know I'm never going to have negative temperature there unless the temperature in the room is negative, or the outside, if we're outside in Alaska or something, it's negative, whatever, Montana, something like that. But what is my maximum temperature? 100. So I want to be just a little bit above that. So I'm just going to do 110. So that's how I'm using the context of the problem to adjust my window so that I can see everything happening there. So here we get a nice picture of the cooling of that particular object. Notice it's flattening out. Where is it flattening out at? What is that number that it's flattening out at? Yeah, because if it's sitting in a room that's 30 degrees, it's going to get to 30 degrees. If it sits there long enough, it's going to get to 30 degrees, and it's not going to go below that unless the room temperature drops. Okay, so it's going to get to room temperature. Kind of like if you leave your cold drink out on the counter in the kitchen, like my kids do all the time. Eventually, it gets room temperature, and nobody wants to drink it. Right. So here we got a hot drink sitting out. Eventually, it's going to get to room temperature. That's where it's flattening out there. So now, if we're wanting to know when that's 50 degrees, I can use that and graph what in Y2? 50. They're crossing, we get the intersect of that. Second trace, intersect, enter. 18, that's that same number that we had, right? On part C, it says verify that answer. We just did. Part D says How much time has elapsed when it reaches 35 degrees? So what do I need to change about my graph? Yeah, change the 50 to a 35, hit graph. Should be somewhere, more over here because it took it longer to cool off to 35 degrees. So we're going to find that intersection there. So second trace, intersect, enter. It's going to take it 39.2 minutes to get down to 35 degrees. Give or take a few seconds, probably. So using that intersect tool, but you've got to be able to solve it by hand to get the cooling rate. Okay. This same formula works if it's heating up. Like if you set a popsicle out into a warm room, the same formula will work. Instead of K being negative, though, K would be positive out of that. So when you think about if you're going to murder somebody, varying the temperature in the room can buy you time or change the time of death, right? So if you could put them in a room that is extremely cold, their body temperature is going to drop faster, right? So that's going to mean that's going to put the time of death earlier, right? Or it seemed like it would be earlier if you can get the temperature to change back to a normal temperature before the body's found, or putting a heater in the room out of that to change how fast the body cools, and then doing that. So there's lots of things that you think about when you watch these shows, and how to get away with murder and all that stuff.
I think you've watched it.
I have watched too many of those, and this stuff just gets me thinking about all those things. And like, how do you get caught if you know math? You could get away with it. Well, yeah. Normally we don't think right. If we're killing people, we're not thinking right anyway. All right. So now, logistic model. Last thing. Logistic model is you're going to get these equations given to you in the logistic model stuff in this section. You're going to have this formula. It's some neat things. So A, B, and C are numbers, constants. A is something bigger than 0. C is something bigger than 0. And if it's a growth model, the B value is going to be greater than 0. If it's a decay model, the B value is going to be negative. Now, notice that there's a negative in the formula. So if B is positive, this negative is going to still show up. If B is negative, that negative is going to go away. Okay. Now, the carrying capacity, what the logistic model does is it's used in ecosystems. Like if you're thinking of, like you work for TWRA, Tennessee Wildlife Resources Agency, certain environments can only support a certain amount of deer. Or it's turkey season right now. There's only so many turkey that can live in a certain area until they start eating up all the resources that they have. Like there's only so much food there, there's only so much water, there's only so much land. Okay? The carrying capacity is how many of those particular organisms can be supported by the environment. Okay? I remember when I can't remember how old I was. It was probably about 13, 14. In the area where my parents lived, which is over toward Good Hope, there was a lot of turkeys on Mr. Tad Tacker's land, and a lot of turkeys there. Well, TWRA came in and said, "Hey, we're going to move some of those," and then they used rocket nets to catch these turkeys. It's the coolest thing ever. If you've never seen it, YouTube that junk. It is awesome. Okay, they baited the turkeys into the field. They had a net laying on the ground over here, and it had rockets attached to one side of it. The other side of it was like staked into the ground. The turkeys got out there, they're eating the shell corn that they throw down on the ground, which they tell you can't do, but they can. And so when the turkeys got in that area, the guy sitting over there in the truck, he hits the button, the rockets go, the net falls over the turkeys, and they catch all those turkeys and they move them somewhere else out of that. Because the carrying capacity for that area was reaching its maximum. and they had other areas they could move those turkeys to and help that population thrive. Okay, so carrying capacity, that's the number on top. Okay, that's how many can be supported in the environment that you're in. Okay, so let's look at an application of this. So here we have a problem. We're talking about carrying capacity. So you got the 750. That's how many. It says fruit fly population, but that's not correct. I don't know why I haven't changed that over the years, but I changed the problem and didn't change the title on the slide. That's okay. Talking about yeast. If you bake bread and all that fun stuff, that happens there. So yeast, 750 grams of it is the carrying capacity for that particular environment. Whether it's the amount of water that you blew the yeast in, or the bread that you're putting that into, whatever it is, it's 750 grams. That's your carrying capacity out of that. So take the carrying capacity, 750 grams. That you don't have to calculate that. You don't have to do anything. It's that number that's on the top of the logistic model. Determine the initial population. Initial means when it started. What is the time when it started? What do I plug in for T for the initial population? How much time has passed when we start? 0. We're plugging in 0 for T. Okay? So we're doing 750 over 1 plus 74 e to the negative 0.526 times 0. So this is going to end up being 750 over 75, which is 10 grams. At time 0, we had 10 grams. What is the population after 5 hours? So what are we doing with the 5? Plug 5 into T, working that out. So P of 5. I'm going to do that with the calculator because I don't do the E stuff in my head. So I'm going to do a big fraction button. I'm going to put my 750 on top. On the bottom, I got the 1 plus 74 e to the negative 0.526. Is that right? And then times 5. Just plugging in 5 for T, working that out. 118.41, so 118.4 grams. Now, I could also graph that function. If I wanted to graph that function, I could put in the fraction into my calculator here, and that's going to help me with D part. We'll do it both ways. And then we'll do 1 plus 74 E 526, and then instead of T, you're doing X. Now, when I graph that, that's probably not the best of window ranges to help me there. So I'm going to hit window and adjust my window. My X maximum, 10 is probably good. My Y minimum, I'm not going to have a negative amount of yeast. Right? I'm either going to have none or I'm going to have some. My carrying capacity is 750. So I need, at some point, 750 is going to be as high as it gets. So I'm going to go a little bit above 750. I'm going to go 800, just so you can see the picture of the graph and see what's happening there. So it's kind of flat here. And then right here, that's my initial time of 0. And I'm going to stretch it out a little bit. I'm going to go to my window and I'm going to stretch out my X maximum. I'm going to go to 20. Just so you can see what a logistic model graph looks like. Because this will come up when we do 6.9. So at 750, it's going to flatten back out. So right here, that's our initial amount right on the y-axis. and then it goes up, and then it's going to flatten out at 750 because that's our carrying capacity. Once we reach 750, we're not going to get above that without some yeast dying off. It's going to get to 751, and then some yeast is going to die. If we're talking about deer or turkey, it's going to get to a certain level, and then you're going to start having issues, CWD, diseases, lack of food. You're going to have some of the population die off because that area can only support so many. So here we got this graph. A logistic model kind of looks like this every time. So I was going to have a flat spot, increasing graph, and then a flat spot at the top. That flat spot at the top is your carrying capacity. Okay. It wants to know population after 5 hours. If I hit trace 5, there's that 118.41. Same number. Okay. So I plug in 5 for X for the time. They want to know when will the population reach 250. So what can I do with my graph to find that? I can graph 250 and see where they cross. Somewhere around 1, 2, 3, 4. A little bit less than 7, but I'm going to hit the intersect button and let it find it for me. Second trace, intersect, enter, enter, enter. 6.86 hours. I think 2 decimal places is probably plenty. Maybe too much, I don't know. 6.86 hours to reach 250 grams of yeast using that logistic model. You could set that equation equal to 250 and solve it, but you can do it with the calculator as well. All right, one last problem. Got a logistic model for wood products. Okay. Here's our equation. The equation is percentages of remaining wood products after T years. The carrying capacity is right at 100. So that's saying that the best case scenario is 100% of our wood products, right? It's a little bit over that right now because of some rounding issues probably along the way, taking our data and finding that equation. So 100%, that's really close to 100%. So we're okay with that being just a tad bit over. If it was a tad bit under, I'd be okay with it too. If it was 99.6 or something like that, I'd be okay with that. That's close to 100. Okay. Now, this is a decay problem because I know that exponent's positive. If it's positive on the bottom exponent, then it's a decay problem. That makes sense because wood products are going to deteriorate over time, right? The wood, if it gets wet, it's no good. It's not good for it. It's going to rot, that sort of thing. So wood products is going to go down out of that. And so here's our equation. Let's find the decay rate. Well, the decay rate, 5.81%. So decay rates are usually in percentages. So we're going to change that to a percent. 5.81%. We're losing 5.81% per year. Looks like T is in years. Okay. What percentage of the wood remains after 15 years? So we can either manually put in a 15 or we can graph that thing and then trace 15. Whichever way. I'm going to graph it because I'm going to end up using the graph eventually anyway. So I'm going to graph that equation. So I'm going to go to y equals, I'm going to put in that fraction. And I've got 100.3952. Then on the bottom I have 1 plus 0.0316 e to the 0.0581 x. And I'm going to clear out that 250. I know I'm going to have to adjust my window because remember we went up to like 800. We definitely don't need to go to 800 here. My maximum amount for this problem is going to be on my window, my Y max. I'm going to put it just a little bit above 100. I'm going to go 105 just so I can see the top there. And then my X maximum, my X minimum, I'm just going to make it -1. My X maximum it's probably going to be a bunch of years. You know, I know we have a wood product in our house. We have a secretary. Do y'all know what that is? Basically, I didn't know either till my wife bought one. It's a cabinet basically, and it's got like a glass door on one side. The other side has a door that opens and makes a desk. Like the door falls and it has a chain on it, holds it flat like a desk, and it's got little like areas to store bills and things like that in it. She puts dishes in hers, but that's a whole other story. But that's a secretary. So that thing is over 100 years old. Okay, so I know wood products can last a long time. There's a big thing now. Over the years we've learned this. I'm gonna go to 150. That's probably fair. That's getting us back to the 1850 or something, 1870. That's Civil War kind of time is where 150 is getting us. So there's stuff that survived since then. Probably older than that too. Let me hit graph. I should be seeing that logistic kind of curve happening. It's flat up here at the 100%, coming down here and flattening out at 0%. If everything decayed away, everything burned up, whatever. Okay. They want to know remaining percentage of wood products after 15 years. So we're going to hit trace 15. 93.34%. Okay. How long does it take for the remaining wood products to reach 40%? So I'm just going to graph 40 on the Y2. They're crossing. We've seen this game before. Second, trace, intersect, enter, enter, enter. 66.55 years. We talked about this already, explaining why the numerator is reasonable. 100, it's close to 100%. It's reasonable because it's possible that all of our wood products survive out of that, depending on what wood it's made out of. If it can, how long it is resistant to disease or bugs or water. Different wood has different properties. Cedar is really resistant to decay. Maple is pretty resistant. Oak is really resistant. That's why you see a lot of furniture made out of oak, because it's really resistant. It's also very dense, heavy out of that. So 100% would be best case scenario. When you buy some of the more modern furniture, it's made out of pine, which is not very resilient. Pine things tend to not last as long, just because pine is just not as dense a wood. It's soft and it breaks apart. All right, so you've got a lot of word problems in this section. So what we're going to do is we're going to you got the rest of the day today.